So we've got a manufacturer of contact lenses, and in their current state, they're experiencing a lot of losses on their high speed line, and they're increasing over time. The challenge has been that traditional RCA methods have not yielded any potential causes. So there is an opportunity here to use a classification tree. We are going to try to predict the cases of defects given a set of inputs, and then also understand which inputs have the most effect on that prediction of a defect. So, how are we going to set up that data set to make sure that we're able to run this classification tree appropriately? The first is we're going to determine our response variable. So over here on the left, we're going to see that the inspection result is yes or no. Yes being it found a defect, no being there was no defect found. And we're going to organize them into a column of data like so. Next, we're going to determine our input variables. At this particular manufacturing plant, a lot of the senior people were considering the oven location and the airflow as the most important factors. You had other voices in the room who were talking about differences in the containers that they had, other months in stock, hours in WIP, lots of different types of inputs that could be affecting whether or not there's a defect. When you have something like a machine learning algorithm, having all of those types of inputs is not a problem because it can handle a lot more data. So in this case, we had 18 different input variables that were included as part of this model. And we just have a small sample of those here. For example, those hours in WIP, whether or not there were additives, the months they were in stock, the condition of the tray, preheating, etc. So now you put all that data into a classification tree, and this is an example of what something you might come up with. You're not supposed to read any of the particulars in this case. It is a large tree. But you can see already that there's a split up here at the top. And as you go down, you can find cases where there are higher proportion of defects at a certain point. So for example, let's say I wanted to look over here and see what's causing this particular issue. If I click on that, I will actually get a list of all of the different parameters that have been applied to make this happen. So we have a parameter one, a generic parameter one in this case of less than 582. The condition of the tray was greater than or equal to 2.5. T component height was less than 13.9. The wall thickness was less than 24.6. And the T component height, again, there was another split that was included on that case, was less than 4.88. And you start to see a higher proportion of defects when you have all of those come into effect. So besides getting the tree output, which is your visual output, your main way you might want to be exploring how your data has led to different outcomes. Another thing that you will start to see with classification and regression trees is the numeric statistics that come out as part of that. So in this case, you get a little bit of information about the responses. So in our initial set, we had 7,816 different observations. They were classified as no's and yeses, and this was the original count and split, just describing the data that you have input into your model. On the right side here, we have some statistics that we can use to assess whether or not our model was effective or not. Similar to when you're running a regression, you have an R squared, and that can tell you how well your model is actually fitting to your data. This is your similar equivalent in a classification and regression tree. So we've got things like accuracy, precision, true positive rate, false positive rate, true negative rate, false negative rate, and the F1 score. You want these numbers to be high, especially for accuracy and precision. And we also want to take a look at different ways of training and testing our data. When you are running a classification tree, usually there is an option to split your data set into training and testing. That way, only some of your inputs and results or observations are being used to create the model. And then you'll use observations that haven't been used to create the model to actually test it out. You want to see pretty consistent results between the two of them. Once you've assessed that your model is pretty good at predicting your responses, you can also take a look at the particular inputs that were effective for those cases. So in this case, for example, we've got a Pareto feature importance. This is a great chart to look at to understand which of your features were used in creating that tree. So for example, the wall thickness, the condition of the tray, T component height, and as you go down, you'll see that some of them were more important than others. And in this case, if we just pull out the numbers themselves, the wall thickness was 30.4%, and the condition of the tray was 20% importance in this case. The airflow and position, which is what the original hypothesis wasn't shown to be as important. So what did we learn in this case? Choosing your input variables and eliminating bias is important, and that you can add many more variables in the case of classification and regression trees than for some other types of models. It also reinforces the importance of a good measurement system up front, as in if you have lots of data, but the data that you're looking for still needs to be collected. For example, the condition of the tray might not be information you already have. Having those good measurement systems up front is important to making sure you have good data to input into your models. The third thing to learn from this case is you actually don't need millions of rows of data. You can start with 100 and then add more. In our case, we had 7,000 rows of data. So you're able to use, even in cases for root cause analysis, you can use fewer cases to at least start the process of understanding where the root causes might be. In this eye contact case, you'll see that the condition of the tray was one of the highest causes for the defects. So that might introduce new policies or new actions to be able to either have higher quality trees or make sure that you're continuously monitoring those cases. After you've run a classification and regression tree to find something like that out, the next step is actually to run the designed experiment to help you prove the root cause. Using the conditions of the tray as an example, you might want to actually run the designed experiment to ensure that those are really the main cause of your defect.